Hello, this is Ron Hardwig, and I'd like to talk to you about my theory on how tornadoes are formed. Actually, I've done quite a bit of research on this. I have a book that I looked at 1,300 tornadoes and saw their relationship with the jet stream. I made a little video before. I called it Tornadoes: How, When, Where, Why They Form, What are their source of energy, and why do they dissipate. By the way, once again, my name is Ronald Hardwig, and you can reach me at rsdata, D-A-T-A-I-N-C, at AOL.com. From all the information that we receive from the meteorologists, they always talk about how the warm air coming in from the south meets the cold air coming down from the north and how it intermixes. That's good. That's the way it starts. As these mix, one of the vortexes within here, there's vortexes formed. As they're formed, though, one of them comes up and is met by the jet stream. We can have a thunderstorm without having a tornado, which I've plotted, where we have nothing but hail. But once one of these vortexes within the thunderstorm reaches the jet stream is actually what causes the tornado. This is caused by what is called the Bernoulli effect, pulling the air out. I'll go a little further here. We'll look at a different map. Here I'm showing a tornado. As we know, it starts out small at the bottom and gets bigger and bigger. The jet stream does two things to the tornado and creates two different things. The velocity of the jet stream going off across the top helps pull the air out of the tornado. But there's another action that I think's been overlooked, and that's what I call the relative area of interface. As a tornado goes up, we know that it gets wider. We can see this physically. But to give you an idea of just what happens, if it was 1 unit down here and the jet stream was here, you would have so much drop in pressure due to the jet stream passing over. But if it was twice as big at the next point, the actual area is 4 times as great. Same thing here. If it was 20,000 feet here, 40,000 feet in diameter here, the actual area of the relative interface is 4 times as much. So a tornado is affected by the jet stream in 2 ways: the velocity of the jet stream and the size of the relative area of interface. Now here I've drawn as an ideal diagram with these just being circles. We see the tornado going off to one side as this is blowing across. But to give you a little idea of what can happen, if we had just a 10,000 foot diameter tornado here, and the tornado on the ground was just 400 foot in diameter, if we had just a 0.001 or 1,000th psi drop at this area, it would equate to a 0.625 psi drop here, or from a standard pressure of 14.7, it would go down to 14.025 psi. Another thing I'm showing here is an action-reaction. Newton's third law of motion says that for every action there's an equal and opposite reaction. In all the other forms that the meteorologists talk about, they say that the thunderstorm or the jet stream, the tornado is just within the thunderstorm. If that were the case, then we would have to see downward force to equalize the action of what's going up in the air. This isn't what we see, though. We see action as it's pulled out, and the reaction we see on the ground as a tornado. Now, I did a little plotting on this, and I looked up 10 EF1s, 10 EF2s, 10 EF3s, 10 EF4s, and 10 EF5 tornadoes. Some of them that we know of: the Joplin, Missouri tornado, the Plainfield, Missouri, Illinois tornado of 1990, the Moore, Oklahoma, just last year of May the 13th, and the one that hit close to my home, the Washington tornado of November the 13th. What I did is to plot where these tornadoes fit relative to the speed of the velocity of the jet stream in knots, relative to how high they are. Now, how high they are comes into play, just like I say over here. The higher it up, the more it fans out, the more of the relative area of the interface, which creates a larger tornado. Now, one thing you got to understand, these will intermix here, because when they go out and evaluate a tornado, they look at just what the damage was on the ground. And from that, they say it's either an EF 1, 2, 3, 4, or 5. So that's very subjective, and we will see some intermixing. But overall, you can see that the EF1s are here, the EF2s are here, the 3s are here, the 4s and 5s are somewhat intermixed, but still, I've drawn a line where the average is. Another thing that I came up without even thinking about it, I wanted to have some basis for those that didn't have tornadoes, but we had thunderstorms. So I looked up 10 hailstorms where we had big hail. Now you'll notice one thing in every case. If it was below about a 58 knot threshold, we had nothing but hail. Above that, we have tornadoes. And I couldn't believe how close it showed. Here's 1, 2, 3, 4 hailstorms, but they didn't meet that threshold, which looks to be about 58 knots. Then you have 1, 2, 3, 4. You have a number of tornadoes here that were just above that threshold, and they did create a tornado. Now what I see happening is just like an atomizer. And I'm going to show you a little experiment here that I can show. This is actually what's happening. A tornado is acting just as an atomizer. I have a little glass of water. Let's say where the water level here is the earth. I have 2 different straws of varying sizes. This one's about twice the diameter of that. If we blow air over the top of it, which would be just like the jet stream, you will see the water come out, which is happening just what's happening in a tornado. That's the small one. That's the large one. You can see the difference. What I'm showing here is the relative difference, as I say over here. So a tornado is related to 2 things, or controlled by 2 things. It's controlled, first of all, by the jet stream in 2 ways, I should say. It's controlled by the velocity of the jet stream and the height of the tornado, so the relative area of interface. So if the tornado is much higher, you have a much larger tornado. Now, I've actually written a book that I'm selling, self-published. As I said, I looked at over 1,300 tornadoes for over about 6 to 8 years, and I have those in here. It's about 130 pages. For anybody that's interested, if they want to get in touch with me, my name is Ronald Hardwig. I am a professional engineer. I am not a meteorologist, but I might mention that my great-grandfather was killed in the tri-state tornado of March the 18th, 1925, of all things on his birthday. So this has always been known in our family, and one of my reasons for always trying to research tornadoes. But if you want one of the books, and I'll include what I have on here as an addition to that, it is $24.95, which includes shipping in the U.S., continental United States. Once again, you can reach me at rsdatainc@aol.com. Thank you very much.